Hello, this is the homework from chapter 11. In this session, we will be solving problems 1, 4, 11, 20, 31, and 45. Let's begin. Problem 11.1 reads, a 120 kilogram, 0.120 kg, 50 centimeter long, so let's go ahead and do our conversion. 0.50 meter long. A uniform bar has a small 0.055 kilograms, 0.055 kilogram mass glued to its left end and a small 0.11 kilogram mass glued to the other end. The two small masses can each be treated as point masses. You want to balance the system horizontally on a fulcrum placed just under its center of gravity. How far from the left end should the fulcrum be placed? All right, the formula for the X center of mass is equal to the summation of X1 M1 and divided by M1 plus X1 M2 ... divided by M1 plus M2 ... So we're going to go ahead and treat these as point masses, and we'll use the left end of the bar for this was 120, let's see. This is left end at 120, this is left, and this is right. And the center of mass at the bar is at 0. So we're going to use the left end of the bar as X equals 0. So we have, first of all, the bar, which is 0.12120 kgs. And then half of that is going to be 0.250 meters. And then left was 0, right? Plus the right is going to be 0.11 kgs times 0.500 meters divided by 0.120 kgs, that's the bar, plus 0.055 kgs, that's at the left end, plus 0.11 kg. And we are going to get a value of 0.298 meters. (11.4) reads, a uniform 300 Newton trap door in a floor is hinged at one side. Find the net upward force needed to begin to open it and the total force exerted on the door by the hinges if the upward force is applied at the center, and B, if the upward force is applied at the center of the edge opposite the hinges. For A, the force is applied at the center of gravity, so the applied force must have the same magnitude as the weight of the door, or 300 newtons. In this case, the hinge exerts no force. And B. The moment arm of the applied door force is twice the distance to the center of mass. So the force is going to need half the magnitude, or 1/5. 150 Newton. So now the hinges have got to supply the rest of the force. So 300 Newtons minus 150 Newtons is going to give us 150 Newtons. All right, 1111 reads, a diving board 3 meters long is supported at a point 1 meter from the end, and a diver weighing 500 Newtons stands at the free end. So we've got something like this. The diving board, the diver is here. This is 300 Newtons. This is 3 meters from end to end. We have some kind of cantilevered system there. And we have, here's the support of the diving board. This is 1 meter right here. And we want to know, the diving board is of uniform cross section and weighs 280 Newtons. So weight of the board equals 280 Newtons. And now we want to, A, find the force at the support point, and B, the force at the left-hand end. All right, so our free body diagram is going to look like this. You've got, here's the board. We've got 500 Newtons going here. We've got right in the middle, we've got the weight of the board, 280 Newtons. And the right here is where the support is. We've got a force going up there, the normal force, or the force F1, we'll call it F1. And then we've got right here, we've got a force going down here. And so we'll call that F2. And this whole thing is 3 meters. And from here is 1 meter. So we can take the sum of the torques about this point, and then we won't need this force, right? So we've got sum of the torques about A. Sum of the torques about A is going to give us F1 times 1 meter. And that's going to be positive. It's going to go counterclockwise, okay? Minus 280 Newtons times 1.5 meters. That's going to produce a clockwise. So we're going to go ahead and call that a negative. And then that torque that the diver is producing is 500 Newtons. That's a negative as well. And that's times 3 meters. And so solving for F1, we're going to get F1 equals 1,920 Newtons. So that is the force at that support. Okay, now to solve for F2, we're just going to take the sum of the forces in the y direction. So sum of the forces of the y direction are going to equal, F2 is going to be, F1 is, we solve that, 1920 Newtons. Okay, that's going to be positive. Minus 280 Newtons, minus 500 Newtons, minus F2, I'm sorry, F2, because that's going down too. These are negative because they're going down. Equals 0. The board is in a static equilibrium scenario. So F2 is going to be equal 1140 Newtons. That was 1111B. 1120 reads, a non-uniform beam, 4.5 meters long and weighing 1.4 kilonewtons, makes an angle of 25 degrees below the horizontal. So we got something like this. And this is 25 degrees. It is held in position by a frictionless pivot at its upper right end and by a cable 3 meters. So this is 3 meters. Farther down the beam and perpendicular to it. So there's a tension in the cable. All right. Finally, the center of gravity of the beam is 2 meters down the beam from the pivot. So we'll have the CG here. And that's going to be, let's see. Lighting equipment exerts a 5 kilonewton downward force. So we've got 5 K-Newton here. Oh, and this was 1.4 kilonewtons. And that is at the lower end of the beam. And how far is it? 4.5 meters. So this whole thing is 4.5 meters. Okay, find the tension in the cable and the horizontal and vertical components of the force exerted by the beam on the pivot. Okay, so for the tension in the cable, we will take the sum of the torques. So we've got T, it's at 90 degrees. So T times 3 meters, that's the tension in the cable, is going to, that's going that way, and that's positive, minus 1.4 kilonewtons times, what was the distance there? 2 meters, right? 2 meters times cos 25, right? The cosine will be the lever arm. Minus 5 kilonewtons times 4.5 meters times another cos 25. And that tension is going to work out to be 7.64 kilonewtons. Okay, I'm supposed to also find this guy is P1 and P2. All right, so P1 is going to be equal to T cos 25 minus 5 kilonewtons minus 1.4 kilonewtons. And I'm going to go ahead and grab that from the solutions. And it gives us negative 0.53 kilonewtons. And this guy, the horizontal guy, is going to be equal to the horizontal component of this, which is T sine 25. This is a negative T sine. It's going minus P2 equals 0. So P2 is going to be 3.23 kilonewtons. 3.23 kilonewtons. That's 1120. Now we're going to solve 1131, which reads, the bulk modulus for bone is 15 gigapascals. So that equals 15 gigapascals. If a diver in training is put in a pressurized suit, by how much would the pressure have to be raised in atmospheres above atmospheric pressure to compress her bones by 10% of their original volume? Or no, 0.1%. Sorry, 0.1%. Given that the pressure in the ocean increases by 1.0 times 10 to the 4th pascals every meter of depth below the surface, How deep would this diver have to go for her bones to compress 0.1%? Okay, does it seem that bone compression is a problem she needs to be concerned about when diving? So our equation is the change in volume divided by V naught, the original volume, is going to be equal to the change in pressure divided by the bulk modulus. Okay, and we know this right here is going to be a 0.0010. So it's 0.1%, so divided by 100 is 0.0010. That's that value. Equals delta P over the bulk modulus. So now we're solving for the change in the pressure. So we've got the bulk modulus times that volumetric 0.0010 times 15. Oh, that's 15 times 10 to the 9th. Oh yeah, that's 15 times 10 to the 9th pascals equals delta P. And that's going to be 1.5 times 10 to the 7th pascals. And I know that 1 ATM is equal to 1.01 times 10 to the 5th pascals. So converting, it's going to have to be 150 atmospheres. That's a lot of pressure change. And the depth increase for pressure. Let's see, what did our book say? 1 second. Okay, the book says that we get a 1.01 times 10 to the 4th, 1.01 times 10 to the 4th pascals per meter. So now I know that I'm going to have, I need this many pascals to compress her bones. So this is 1.5 times 10 to the 9th pascals divided by 1.01 times 10 to the 4th pascals per meter. And that's going to leave me with 1,500 meters or 1.5 km. I'm not sure how deep divers go, but that seems awfully deep. That's like almost a mile down there. All right, that was 11.31. 11.45 is pretty complicated, but we're going to go ahead and do 11.45A. We're going to solve for the tension in the rope. A says, mountaineers often use a rope to lower themselves down the face of the cliff, called rappelling. They do this with their body nearly horizontal and their feet pushing against the cliff. And that is so wrong how they have this. We put the rope in our waist. I do this a lot. We don't hold on to it because what happens if you lose the grip? The rope actually attaches to your waist, not your hands. That would be quite dangerous. But anyway, we'll solve the book's problem. I can tell they've never been mountaineering before. Anyway, I digress. Suppose an 82-kilogram climber who is 1.9 meters tall and has a center of gravity 1.1 meters from his feet. CG is 1.1 meter, and he is 1.9 meter tall. Rappels down a vertical cliff with his body raised 35 degrees above the horizontal. He holds a rope 1.4 meters from his feet. So rope is 1.4 meters from his feet. And makes an angle of 25 with the cliff face. So 25. Okay. What tension does his rope need to support? All right, so here's the deal. Here's the cliff face. Here's the rope. This is 35 degrees. This whole thing is 35, and this, where he holds it right there, is 25. All right, and so this guy is 10. All right, that's his hand, or that's his hand, yeah. This is very confusing. This is his face, I suppose, and his hands are down by his side. So this is 10. Okay. All right, so here we go. The sum of the torques equals 0. So we have the sum of the torques about his feet are going to be the sum of the torques about the rope. Let's see, yeah, about here. Is going to be the tension in the rope times 1.4 meters is where he's holding it. Cos 10. That's this guy. Between his face and his hands, the 10 degrees. All right. That's producing an upward force minus the weight times 1.1 meter. That's his center of gravity, times cos 35. That all equals to 0. So the tension is going to equal to the weight uh, 82 kgs, 82.0 kgs times 9.8 meters per second squared times 1.1 cos 35 divided by 1.4 cos 10. And that's going to be equal to 525 newtons. And that concludes chapter 11.